All right. Hello, everyone. Good morning. At least it's morning where I'm at in beautiful Colorado, Colorado Springs. Might be a different time where you're at, or you may be in the future watching a recording. But for those joining live, thank you for taking time out of your day to check this out. Today, we're going to go through basic hydraulic theory and the need for pressure boundary conditions. Really, we're going to get down to the fundamentals of fluids. That's really what this means. My name is Walt Prentice. I work here at AFT, do a bunch of different things. Most importantly to you right now, most relevant to you is that I present webinars. So that's what we'll go through. Okay, so today's agenda, what we're gonna do is we're going to begin with the source of all truth, start heavy. We're gonna go through some static and stagnation pressure, might be something you've come across. We'll get into that in detail, go through some examples in Fathom, and then there is a very specific message that will appear in Fathom. At some points, you probably have run into it where something pops up that says reference pressure needed. So we'll go through why that happens and what to do about it. So I hope you all are ready for big brain time. You are going to learn a bunch of stuff in here, things you probably have already learned, but it's good to review, especially when using software, because software is a tool. It is not magic, it is a tool. So the more you understand what the software is doing, the better off you are, the more you can impress your clients and employers and all that. Okay, so we're gonna start with the source of all truth. So you thought you were attending a webinar on hydraulic theory on fluids. Well, actually, I just had good marketing and clickbait to get you to join because you wanted to learn about fluids. But in reality, we're going much deeper. We're actually learning about the meaning of life. And on this discovery, you have to understand we have an overlord. That overlord is Bernoulli. He is our master. He chooses who will go and who will stay. He chooses everything. That is the foundation of everything we do in fluids. So here we have Bernoulli's equation. This is something you probably have seen, at least at some point in your career. I hope so if you are a hydraulic engineer. But let's break it down just a little bit. So first of all, Bernoulli's technically does not include a friction term, so we call this Bernoulli's with friction. I will be referring to this as Bernoulli's equation through the webinar, and I understand technically it's not because Bernoulli's does not account for friction. It's modified essentially because we live in the real world. The way it works is you have some pressure, potential energy, and kinetic energy on one side of a pipe, and then on another side, you have the same information, but something would have changed between the two, okay? And then to balance everything out, because we live in the real world, we got friction. We have pressure loss due to friction specifically. So all of these things are in balance all of the time. This is the source of truth. Oh. Now we can remake this equation if you substitute some things out, because we know we're at steady state and mass flow is equal to density times area, cross-sectional area times velocity. So you can plug that guy into this term, and you pretty much just get a different way of writing the same equation. You can do the same with flow rate. There's many ways you can write this equation, but we're going to focus on the one that deals specifically with volumetric flow rate, just because that's something typical for engineers to worry about is flow rate, not necessarily mass flow. Mass flow is the foundation. That is what is truly balanced. Volumetric flow is not balanced, right? Mass is balanced at steady state, but most people, talk in terms of volumetric flow rate. That's what you measure and all of that. So we'll go through it. Everything with this in mind. So before I go too far, I guess let's make sure we understand the terms. So I said this is all pressure, kinetic, and potential energy information. More specifically, this is your pressure. This is pressure at a point, what you think of as force over an area, what's pushing outwards on the pipe wall. Then we have kinetic energy, velocity squared term. So this is how describes the energy associated with the moving fluid. And then we have potential energy, which is about an elevation. Really what I think of as pressure and this elevation are potential energy. And then kinetic energy is the velocity term. So just like anything else, it's a relationship between potential energy and kinetic energy, okay? All right, now let's see Bernoulli's in action. Let's get excited. We'll do an example inside of Fathom, something I didn't mention. I should have mentioned in the agenda. All of these examples and the context of this webinar is in AFT Fathom, incompressible fluid modeling, pretty much liquids, but the same ideas apply to all of our software, to all of fluids, under the same, if you have the assumption of steady state, I should say, it's the same idea in gases. It's just your equation no longer looks like this. It's a little modified. It becomes more of a differential equation. Velocity isn't held constant, but the idea is the same, where you have an equation governing everything. And it has to do with pressure, kinetic energy, and potential energy, okay? All right, so let's move into our example. Swap on over here. So what we've got is a straight pipe with a constant area. This is a 4-inch pipe, and we're moving fluid from 200 pounds to 180 pounds. I'm in the US. I am the master, along with Bernoulli, of this webinar, so I get to choose units, and I chose our imperial units. So sorry if you're not as familiar, but the same concepts, of course, apply in any system you're in. All right, so what I did was I have a fluid that is water, so it has a certain density, okay, and I have pressure boundaries. The whole point of this webinar is to help you understand the need for boundaries. So if we try to match this system with this equation, let's see if we can piece it out. So one, we have a pressure 1, neat. Okay, then we have a second pressure 2, neat. It's a constant area pipe, which means velocity in and out is going to be equal because it is a liquid, because it's incompressible, and density is assumed to be constant. Okay, velocity in and out is equal, so they cancel out. And in this case, I've kept elevation constant so as to just make it simple. That also then cancels out. So really what we're dealing with is a pressure in, a pressure out, and then frictional loss between the two. It's about as easy as it can get. This is all we're doing in the software, is solving this equation. Now, when it comes to boundary conditions, what this term means is really the edges of your model that allow you to solve everything in between. So the edges of our model here would be our pressures, okay? You have to define pressures in order to solve Bernoulli's equation. At least, well, you have to define two out of these three. You have to define either 2 pressures or a pressure and a flow rate, because it needs, it's a fundamental rule of algebra. If you have one equation, you have one unknown to solve for. So in this case, we defined our pressures. These are our boundary conditions. And what we're looking for is Q. So this is our one unknown. So again, rule of algebra, we can solve for this. And yes, this is how we make money as a software company, is we solve that bad boy. We can run the model. We get output because of it. We can get this flow rate, and because we know other relationships like flow rate to velocity, we can also get velocity and mass flow and pressure drop and many other things by just having defined these boundary conditions. This is a very simple example. You could do this by hand. One thing I didn't mention that is input is the friction factor. Here is another equation where you get a friction factor via another equation, Darcy-Weisbach, or you can enter one in explicitly yourself. But for the sake of what I'm talking about, we're just going to assume the friction factor is known, but it itself is another equation you can solve for, okay? It's based on Reynolds number and roughness of the pipe and all that. All right, cool. So hopefully everyone's tracking with me. I'm gonna try to keep an eye on questions, see if anything pops up, just because understanding these fundamentals is so important. Let's see, it looks like no questions, so we'll be good. All right, so the next topic to go through is when defining a boundary condition, you need to define whether it's a pressure boundary, whether it's a static or stagnation boundary condition. condition. That's something I didn't even mention yet. In that example, I had to put something in, but I didn't tell you what it was. That's okay, we're building up. So many of you have probably not even heard of what the difference is. Honestly, to me, it's a very confusing term because static and stagnation both sound like something that is stationary to me. So I kind of have to get that idea out of my head when I'm thinking about static or stagnation. If there's nothing else you learn from this webinar, this slide can be very useful to you, and I urge you to learn this part. Static pressure is the P term of Bernoulli's. It is the thermodynamic property. It is what you think of when you think of pressure. It's force over an area. It's what's pushing outward on the pipes. It is, so it's what's, in all of your studies, you probably just have thought of pressure, and that's what this static pressure is. You measure this with a pressure gauge. So if you're out in the field and you're measuring pressure, you're measuring static pressure. Stagnation pressure is the combination of static pressure and this velocity, also known as velocity head. It's the combination of the two. That's all it is. And why we do that? Well, it's a convenience term, it's a combination term. It makes solving math a little easier sometimes, but it's also, it captures more of the story of Bernoulli's. If you're looking at the pressure drop, well, static pressure is not the whole thing because you might have a change in your velocity and kinetic energy. So stagnation pressure drop might be more important to you, but it's just a combination of terms, okay, pressure and velocity. And the way you measure this is with a pitot tube. So what this represents, this pressure and velocity combined, is like you have a moving fluid. What would be the pressure if you suddenly stopped that fluid? And that's what you measure with the pitot tube, is you convert, not only do you have actual pressure acting in all directions, you also have velocity moving. And with a pitot tube or a pitot probe, it converts that velocity into pressure and potential energy. So it's a higher pressure than what your pressure gauge would be reading. So the picture here is showing you the difference. You have static pressure, which is just what you think of with gauge, and then stagnation pressure accounts for the velocity as well. Usually it's not as dramatic. Liquids tend to move more slowly than things like gases. So the velocity head term is not as high all the time. But anyway, it's just a picture, okay? When do you use a static pressure boundary or stagnation pressure boundary? You use static when the fluid is flowing at the boundary, because when you're putting in a static information, it's like, it's as if you read a pressure gauge, so you know the pressure of this system that you are now modeling. But because the fluid is moving, you have to say that's a static pressure because we have to assume there's other velocity that we just don't know, but there is a velocity. You use a stagnation pressure boundary when the fluid is stagnation pressure boundary when the fluid is stagnant, meaning a lake, a tank, the ocean, something that is stationary fluid, because when the fluid is stationary, and you know a pressure, and you know the velocity, because guess what? The velocity is 0. So if you're telling the system, the software, the pressure of a stagnant body of fluid, you need to say it's stagnation pressure because it will, because that is truly what you measured. You measured the stagnation pressure without realizing it. It's just that the velocity is 0. So this is the important part of the slide. I was saying that if you learn nothing else, learn this, okay? I'm gonna circle these just for emphasis. When the fluid is moving, you use static pressure. When the fluid is stagnant, like a tank, you use stagnation pressure. Cool? Cool. Now let's look at that in action. Let's see that. Maybe we'll even do an instant replay of the same example. Okay, so it's the same example I have up here. The difference is on one pressure boundary, I have defined a stagnation pressure now of 200. And what I did previously was actually a static pressure of 200. So I have stagnation here, and then I have static here. Okay, what does this mean? Okay, well, let's look at our overlord, Bernoulli, and see what he has to say about it. So stagnation, that means I'm saying that at the boundary, I know both pressure and velocity equal 200 pounds, that is. Okay, and then at my outlet boundary, I just know the single static pressure is 180. We're going to again assume elevation is constant. Elevation's constant, so those can cancel out, and then we have our friction information, length and diameter of the pipe to input, and then we'll find Q. Now, this is a little different than the previous equation because now we have velocity included. Velocity still would cancel out with the outlet, but you don't need to cancel it out because we have another relationship between flow and velocity, another equation to reduce our degrees of freedom. So the way that the software solves this is it knows a stagnation pressure, knows it's 200. As soon as it enters the pipe, there's a gain in velocity and there's a sudden drop in static pressure, but it can still solve this equation. It still solves everything just fine. It'll find a flow rate. It'll find your actual static pressure at that inlet, so it'll total up to 200, but your static pressure will be a little smaller and your velocity head or your dynamic pressure will be a little higher. And it can still solve all of this, and it knows a relationship between flow and velocity again, so it is solvable. Now we look at the output. What do we find? Okay, well, let's zoom in a little bit maybe. So we had a stagnation of 200 in and a static pressure out of 180. What we see is the stagnation pressure in, which in our software is denoted with a naught, so P naught that's stagnation. What am I trying to say? Static pressure. Our static pressure in is a little lower than 200 because, again, as soon as it entered the pipe, it gained velocity, had a little bit of a drop in static pressure. It's very small, negligible, because liquids tend to move not with much velocity. They have a high density, but not much velocity. This becomes very important when you're dealing with something like Aero, which is our compressible flow solver. Again, it's the same concepts here with some extra math, and these differences really turn into differentials. The same concepts apply, and it's important to pay attention to velocity in gases because they can get busted. They can move really quickly, and that does affect your static and stagnation pressure. In Fathom, it's not as noticeable. Okay, cool. So stagnation, what does this represent? I think this represents a lake or a tank or something. And then down here, when it's static, it represents the rest of the pipe. Or it's a junction and it's going into a header or something like that, but the flow is moving, it's not stopped, okay? All right, let's see. I have a question here with copies of the slides post-webinar. Hey, Chris, okay, so I got a question about providing the slides after the webinar. I can certainly get that to you, Chris, okay? Thank you. And then Emily's asking, so inlet and outlet hydraulics. If the fluid is moving, so this is for Emily's question, for pressure relief device inlet and outlet hydraulics, would you recommend using stagnation or static pressure for those calculations? This is a hard question because it depends. But if the fluid is moving and you have your pressure relief adjacent, on your pipe where the fluid is moving, it will be a static pressure set point. But then on the atmospheric side, this is all stagnation out here. This is a stagnation pressure. The atmosphere, it happens to be a gas, but it's not, don't think of it as a fluid, a moving fluid. It is a gas, okay? And Tanae, okay, so another question about the slides. Yes, I can send you all the slides, no problem. And so Emily, also feel free, there'll be some contact info at the end of this webinar where you can email into our support team and all that. You're welcome to ask these kinds of questions and we'll answer in a more specific way for you and your system. But okay, cool. Thanks, guys. Keep it engaging. All right. Oh, wait. One more thing on this example specifically. So we're looking at stagnation or static, awesome. Another thing to consider that we haven't yet is that, okay, well, we defined pressures or stagnation pressures. Cool. What about if we instead define a flow? Well, let me ask you, no one can respond to me, that's okay, I'll talk into the void. If you just put in a flow rate, what other info would you need? Let's assume velocity is out, elevation is out. If you just put in a flow, what do you need? Well, you need at least, actually not at least, you can only choose one pressure or the other, okay? So if you're defining a flow boundary, you have to put in one pressure at least. So what we can do is make this example, but instead have a flow rate boundary condition. And what we did was what I just said, where you have a flow rate, but you still need to know one of the pressures. So because this is an outlet flow rate, then I need to know my inlet pressure. I will get the exact same solutions as my previous example because everything else is the same. So you might ask, well, Walt, how am I supposed to know if I should use a pressure boundary or a flow boundary? You don't always know. It depends on what you are comfortable fixing. Do you know this flow rate for a fact? That's what you're fixing in all of your scenarios and all of that. So cool, put a flow rate in. Is it a pressure? Meaning you know a delivery pressure, you know it's going to a tank, well then use a pressure boundary condition. This is one of the jobs of the engineers to figure out which one. So in this case, we know we have a flow rate and we know we have a pressure, so then we're going to solve for P2. Now again, the solution will be the same as before, with the little caveat that I rounded. So there's a little bit of a little tiny difference, but it's because I rounded the flow rate. What I did was I took the flow rate from my previous example and put it into this flow rate junction, and running the model, I should get the same pressure outlet. So you can see my static pressure is 180. Okay, I didn't put that in anymore, right? The software solved for that, but it happened to be the same answer because we're solving the same equation with the same inputs. It's just a different variable we're solving for. Think of it as just this algebraic equation, right? It is a little tiny different, it's just a little different because, again, rounding, but the solution is the same. Okay, all right, boom. Now we get to go through more examples. Okay, so let's see what we'll start off with. So we did the stagnation, we did the flow rate. Now we will move into our more interesting topics where we go through what I call more internal boundary conditions. Internal. That's kind of weird because it sounds like an oxymoron, an internal boundary. What I mean by that, let's see. So, well, I guess first describe the system. We have a similar system, right? We have a boundary here and we have a boundary here. And what we're doing now is we're changing the system by adding in a control valve. And this control valve is forcing it to be 200 gallons per minute. It was 288. Now it's 200 because a control valve will restrict flow. It will control it down to 200 in this case because that's what I set it to. I said, hey, be 200 and it will. By fixing this flow rate, what you are effectively doing is setting up two different systems. I know you probably didn't see this coming, but I got a big reveal here. What you do by adding in a control valve is effectively splitting the system in two. This is not exactly how the solver works, how the math behind the scenes works. The math behind the scenes is a little different, but this is how I picture it in my mind, and it really helps me out. And it's going to be important when we get to reference pressure. When you have a control valve, or really anything that says it has to be a flow rate, okay, well, what you did was you just set up two systems. Just it happens to be that where the control valve is, it's just a flow boundary, right? So this 200 gallons per minute is really splitting the system in two. And we can solve Bernoulli's for each portion of the system. You just solve it two times essentially. All right, with each P1 and P2 means something different in each case. P1 and P2 is just a reference for upstream and downstream. So that's different in each pipe here, but that's all it's doing. And what we'll see is that, okay, so we can solve Bernoulli's and we will get an outlet pressure here. So we'll say this is P, I will just say P out. Here, we'll solve Bernoulli's on this one and we'll get a P in, okay? By solving Bernoulli's on each side, we get these pressures that are solved for, and then by knowing those pressures, we look at those and that's our dP of the control valve. So let's look at our report. So what I mean is we solve Bernoulli's here, okay? We get a pressure out is 195, a pressure into this one is 185. What's that dP? Oh, that dP is 10, right there, boom, okay? So you can think about a control valve or anything that forces a solution to be a boundary condition, or at least in this case, like an internal boundary condition, because it's in the pipe, but it acts the same way. So that difference is found, it matches up, I guess, is the way to think about it. It's causing 10 pounds of pressure drop in order to restrict the flow enough. There's so many ways you can think about things, but when it comes to boundary conditions and important topics like control valves, this is how I reason through it. Now we can do a very similar thing. Oh, okay. Let's see. Thank you. I'm sorry, I have a question, so I just want to make sure I address it. Tank pressure will be the column of the liquid, stagnation pressure for the tanks at atmospheric pressure. I'm not sure if that's much of a question, Daniel. Tank pressure will be the column of liquid. Yes, correct. Yes, yes. Okay, well, we can talk more, Daniel, if you have a question out of that, but you can reach out. All right, so let's move on to from a control valve into a pump. Oh, we got to put this back so we can do the reveal again. All right, so now we have a fixed flow rate pump, very similar to a control valve, meaning we're fixing the flow rate. It has to be 400, and as you maybe can tell, we are upping the flow rate from 200 to 400. It's greater than the natural hydraulics would want to be. The natural hydraulics want to be 288. So if we want 400, we got to pump it up. We got to add pressure to that system, pump that. Now, because we're fixing the flow rate, and I'm doing this, there's a few ways you can fix the flow rate of a pump, but the way I'm doing it is I'm saying without any head curve, nothing like that, it's just a flow rate. I am putting in 400 gallons per minute. There's no other pressure info, it's just 400, it just is. Very similar to a control valve in that sense. Now what we're doing is like we were with the control valve, big reveal, is we're splitting the system in two, and we're solving Bernoulli's on each side of the system. The difference is this pressure is going to be less than this pressure. That's really the only difference, but that is found out by solving Bernoulli's on each one of these. And it's less than because we have, in order to get 400 gallons per minute, let's say on this side, this pressure has to be pretty high. It has to be much higher than 180, right? And in order to get 400 gallons per minute on this side, the pressure has to be much lower than 200. So it works out that the pressure at this point is less than the pressure at this point, which is why you have a pump to pump it up. So very similar to the control valve again, where you can think about this as splitting the system in two. All right, so now let's look at our results. So you trust me. Here we have a pressure out of the system is 182. The pressure into this system is 199. Oh, that gained pressure, which means what do we need? We need a pump. That pump is providing that 17 pounds of differential in order to meet that flow rate. Okay. All right, say K a lot as if you can respond, but you can't. That's okay. You can ask questions though. All right, now moving on to something else, branching. We're getting crazy now. Moving from single pipe examples upward to 3 pipe examples. Might not seem major, but actually is a pretty big jump. So in this kind of example, what are we doing in the software? How would you do this by hand, essentially? Like, how could you do this? Well, I'll tell you, first of all, this is a solvable problem. You guys have used Fathom probably, so you know we can do tons of networks and all that. The way it works is We know a boundary here. We don't know the pressure or the flow rate here. We don't know anything about here. Not nothing, but we don't know the pressure info here. But we do have these boundaries down here. Okay, so it seems like we have a lot of unknowns, but the beauty of solving systems like this is, yeah, we have a lot of unknowns, but we also have a lot of equations. You can have, I think, depending on how you write this out, there can be 9 unknowns and 9 equations. Unknowns would be like this pressure here would be one pressure, one unknown. You don't know the velocity, you don't know the flow rate, and you do that times 3 for each pipe. That's 9 unknowns. You can reduce those degrees of freedom by adding more and more equations, because you have a Bernoulli equation for each pipe. You have a relationship of velocity and flow with each pipe. And the most important thing to know is that Bernoulli's is all about a momentum balance. At this point, you know 2 things. One, you have conservation of mass because we're at steady state. So whatever's coming in is coming out. That's one relationship. So that's M1, oh gosh, am I really writing this out? I guess I am. M2 plus M3, okay? Or if you have constant density, then you can say flow rate in is flow rate out and add up all the Q's, okay? That's one thing we know about this branch point. The other thing is we know that the 1/2 of this totality of momentum has to balance at the branch point, meaning the pressure, the combination of pressure, velocity, and elevation all have to match. Usually at a branch point, elevation, they're already constant, like it's just a split, so the elevation, you don't worry about that. It's just pressure and velocity. So stagnation pressure has to balance at a branch point, assuming no pressure loss. If there is pressure loss, okay, well, that sounds like another unknown, but guess what? You have another equation to help with that because you have a loss relationship. You know pressure loss because of velocity. So even if it wasn't lossless, a branch right now is lossless. There's no delta P. Even if there was loss, what you did is you add another equation though to be able to solve it. So it's still solvable. But you can do Bernoulli's on all 3 of these, matching up all of these equations, set up a matrix, and get answers. Just like we had with a single pipe, it just becomes more complicated because the more pipes you have, you're just dealing with a lot more equations, but it's possible. That's kind of the end of the story. It's possible. So here we get a flow rate, 133, splits to 67 and 67. You say, well, that doesn't quite add up. Yeah, well, it's rounding. Okay, so it's if you looked at this, I think it's probably 66.5, adding up to 133, or something similar to that. But it does balance, I can assure you. And again, the whole story of this, the story is that you have a balance, but another part of that is you have to define these pressure boundaries. You have to. It needs these in order to make the equations solvable. And it can either be a pressure or a flow, but you need to define something. And it's either, again, either pressure info or flow info. Now we're going to get into a topic that might be painful, might have caused you pain in the past because you're like, what's going on? And that's this reference pressure needed message. To preface all of this, we're dealing with a very similar system. But what we've done is now it's not branched, it's just a single, just think of it as a single pipeline, all constant diameter. So we're getting rid of the matrices, thank goodness. Same system, but we're pumping up something. We're pumping up the water, and then we're, I don't know, pumping down, dropping the pressure down with the control valve. So we're pumping up, pumping down, same system. And what I've done is I've defined this pump with 400 gallons per minute. And this control valve is set also to 400 gallons per minute because as a smart engineer, look, I know steady state. I know 400 in has to equal 400 out. Excellent. And I see a question from Stephen, so I'll get back to you after just a sec. Okay. All right. Now let's try to, so again, this you might think is solvable. I have boundary conditions, I have friction information, I know a flow rate, so it's just gonna split up my system. Cool. Oh, well, you might have run into this message. Okay, so let's digest this. I have a reference pressure issue. Fathom needs a pressure to be defined somewhere in the network. Okay, I do though. I have this one and this one. So what's going on? Okay, but it tells you specifically where. So downstream of my pump and upstream of my control valve, I have a problem. Okay, so what it means is in this area, I've got a problem because it doesn't know pressure info. And that might throw you off and confuse you because maybe in your system, you know it's 400 gallons per minute here and 400 here. But it is not solvable. And I'll show you with this system representation, where if you think of the idea of splitting up the system, you will start to see why it's a problem. So if you take your flow pump where it has to be a flow rate, and we do this idea of splitting it into two systems, right? Okay, cool. Fine and dandy. This one's definitely solvable. Awesome. Okay. And then we take this control valve and split that into its two systems, because again, it's a flow rate, so it's a fixed flow. And then you have this boundary condition. Awesome. This one's also solvable. The problem is in the middle here. Well, actually here, do red to burn it into your memory. That's bad. No, I'm just kidding. It's not bad. It's just something you have to understand. In this subsystem, we have only defined a flow rate. And yes, it's the same flow rate because you as an engineer, you understand in and out. Awesome, good, in and out. The problem is Bernoulli's is now underspecified. There's an infinite number of answers because you've told it a flow rate, and let's just get rid of these terms. You told it a flow rate, and we'll just, friction, whatever, just, it's part of the flow rate, but you didn't tell it one or the other of the boundary conditions it needs. So it's stuck with one equation and two unknowns. There's an infinite number of answers here. So the way I think about it is, sure, you know a delta P, you know P1 minus P2 can get you a flow rate, awesome. But what is P1 and P2? You cannot tell for certain what the actual values are. There's too many unknowns, which is why you are required to enter at least one pressure information to make this equation solvable. Okay, cool. And just by the way, I've got some questions on T's and branches and all that. That's awesome. I'll get to that right after I go through this reference pressure stuff. Okay. All right. So you know flow equals flow, cool, but that's a trivial input. It already knows that. Fathom already knows that 400 equals 400, like 400 will be in and out. Telling it twice doesn't help. There's an infinite number of answers. So let's say the delta P needs to be 10. Well, is it 190? Or is it 50 and 40? Is it 1,000 and 990? There's infinite answers. That is the root of the problem. So it's not solvable. I'm going to run this and it's going to say I can't. And it's, again, the pump and the control valve. And then with this system, because I've split it into subsystems, it confirms again that the problem is the middle subsystem of I don't know any pressure, so I cannot solve this. Okay. So before I get into, well, actually, let's keep going. Okay. So here's a summary. You get an error, not an error, a message. And it's important to understand it's not a limitation of Fathom, just his math. Blame Bernoulli. He's the master, right? We're just his servants. So when we take this system that is both flow and flow, you think of it as splitting into two systems, sorry, three in this case. And this middle one has no answer. There's no solution via Bernoulli's. And this is a better way to visually see the equation, is that you know a flow rate in this middle part, cool, but you don't So you know a P2 minus P1, but you don't know a P1 and P2. Awesome. So I've told you the problem. I wouldn't be a very good host if I just went away now and let you deal with it. So I'll show you how to fix this, but it's important to understand why it's happening, because then you can get creative as an engineer to figure out what the heck to do. So one thing to do, so the goal is we need some pressure info somewhere in here, somewhere. So one resolution I had was, what if instead of having this be a flow control valve fixing a flow rate, what if I instead fix it to be a pressure drop that seems reasonable to me? I think it's 10 pounds. That's a reasonable pressure drop. Okay. It already knows it's going to be 400 gallons per minute because the upstream pump is 400 and it's steady state. By fixing this pressure drop to be 10, it now has enough information because it knows a flow rate through the whole system. It knows this boundary. It knows how much it can pump up because you're going to pump down, take away, at least via the control valve, by 10, and it is solvable. Oh, I guess I don't need to run it, but whatever, I'll run it. There we go. So it's runnable. Awesome. And we get the information, we get all the information from solving the Bernoulli's equation from three subsystems. We have a pressure outlet and it can work backwards. It knows a flow rate. So because it knows a flow rate, it knows it solves Bernoulli's to get an upstream pressure here. And because I told the control valve you had just dropped 10 pounds, it can work backwards and add 10 pounds, right? So it was at 199, now it's at 209. It knows that because I told the control valve to be that. And again, because it knows this pressure and a flow rate, it now can do Bernoulli's up here to find this pressure. This pressure in is 209, and it knows this pressure, and from this part of Bernoulli's, it knows a pressure and flow rate, so it knows this pressure, so it knows a total DP across the pump. It knows it has to be 27, and I didn't mention this before, it reports a negative DP because how we define DP in Fathom is all about pressure drop. So if you're pressure gaining, it's a negative. So you got to kind of trick your mind a little bit to gaining. Okay. And if you actually look at this, if you look at the combination of these two, what's negative 27 plus 10? That's 17. It needs 17 pounds of pressure rise. If we go to our pump example, oh, it was 17 here. It's just what we did was we added and took away, but the DP, the net DP is still the same. It's kind of an interesting fact. You can think of this as one pump, right? It's just this pump has to add more because you're taking away. Inefficient, you can think of. But it's able to solve this by working through Bernoulli's in each part of the section. Now I have a relevant question from Amir. How do you split a model? How do you split a model in the software? You don't. I am doing this as a representation. You won't go through and just say, hey, Fathom, right click split. That doesn't happen. I have this model and then I built out the second set of submodels as a representation, just to show you this is kind of what it's doing. This is how it's thinking. So don't yourselves go through and try to make split models other than for experimentation and trying to learn and understand. This is not effective use of, don't do this when you're actually modeling systems. Don't do this. This is just to show you what it's doing, okay? All right, so we did that with we fixed the problem by telling it instead pressure information instead of flow information. Well, we could also solve this reference pressure issue by instead of just having a pump with a flow rate, is we have a pump curve. What this does is it now matches a flow rate with a head rise or a pressure rise. And by adding this extra information, we've now reduced the degrees of freedom and we know how to solve the problem. The way it works is very similar to a control valve. So let me just go out to the visual report. What does the control valve do? Sorry. The control valve is still set to flow. So it's different from the other scenario, right? It is a flow rate. Because it knows it's 400 gallons per minute, the whole system is it's one pipe. We look at our pump curve, 400 gallons per minute. We're a little out on it. That's all right. We're about 65 feet of head, which translates to a pressure of, I don't know, 20 some. Let's see, I guess we'll look at our output, 28. So, sorry, the way this works is we have a known flow rate through the whole system. We know it's constant in each subsection, right? It's 400. So in this part, we can solve Bernoulli's and get a pressure out here. Because we know this pressure inlet and we know it's 400 gallons per minute, we can match it on the pump curve and say it needs to add 28 pounds. So then because of the pump curve, it knows my inlet pressure here is 210. So that's one boundary of the new Bernoulli's for this part, okay? And it knows also a flow rate of 400, so it can solve the pressure here. It knows the pressure out is 210. And again, in the subsection, it knows the outlet pressure and the flow rate. So it finds the pressure here is 181. So you have a total DP across the valve, sorry, is 199. Total DP is about 11. So again, it can solve everything because you gave it a curve or pressure info, and that could be done with a pump curve. It could be done by changing the control valve definition. It can be done actually a lot of different ways. The problem is there's so many ways you can trigger a reference pressure issue that it's hard to just boil it down into, oh, this is one example of it, because there's so many things you can run into. But it all comes down to this same idea that you have not given it enough information to solve. And in order to be able to solve, you need to give it pressure info somewhere. And that's either the control valve or the pump, or replacing a flow boundary with a pressure boundary, and then it becomes solvable. I like to work backwards in these things. Okay. P out, in and out, both 210. Ah, thank you. So Heath is asking, why is P in and P out both 200? Excellent question. This would be because it is a very short pipe, and also, so we're just not going to the, we're not going into deep significant figures here. So let's see, let me see exactly. It's 5 feet. I think velocity is about 7 or something like that. There's not much pressure drop that happens in 5 feet. Let's see if I can get you let's show digits. Usually I like to keep things simple for the sake of not hurting your eyes, but let's bust out the digits. So here you can see now, Nita, that in, it actually is not just 210 and out is not 210. There's a little bit of pressure drop. It's just small because it's a short pipe. Cool. Now let's get rid of that because I don't want anyone to be scared of all the digits. Okay, sweet. So that's most of the topic for today. I'll go through a quick summary, but there were 2 questions I want to. Oh yeah, you're good, Nathan, no problem. It is on the pipe. It's a little strange, but this outlet in and out is not the pump. Sorry, the in and out is for the pipe, and the DP here is for the pump. So there you go. There are a couple questions before relating to T's. So let's go to this branching example. How do you fold in loss coefficients for something like this, a branch or a T? So first of all, this is a branch, and by default, it is lossless. You can add loss information by telling it K factor in and out is one thing. Thanks, Subhasis, no problem at all. Okay, so you have a branch point here. It's lossless. You can put in K factor information if you want to in a branch. I don't know if I've ever seen many people do that actually. Most people will use a T-junction or just assume it's lossless, because if you have a big system with a lot of pipe friction, the losses through a T can be insignificant compared to the loss through the whole pipe. So sometimes you're just fine ignoring it completely, but another way is to add a T. And the T, actually, I'm gonna create a child T, and I'm going to morph this guy into it. Yes, I know. And let's change the orientation. And what you can do is you can add in loss factors via correlations that we have gotten from literature. This is one way to approximate loss through a T because it's just from literature. So is it perfect? No, but it's something. So that's one way, or you can do K factors. So I hope that answers your question. Let's see, who asked that question? Stephen, that was Stephen's question. All right, Madison had a question about what is the benefit of using gray circle versus using a Y fitting or a T? So similar concept. Why would we use a branch instead of a T? To simplify. A branch is assumed lossless from the beginning. It can also, you can attach many pipes to this guy. You can attach up to 25 pipes if you have, like I've seen gas turbines with a lot of branch points. A T is limited to 3 pipes, but a T will incorporate loss information if you want as well. So it just depends on what you're looking for. I like branches and starting simple, looking at results and then working my way up to include T loss. But a lot of times these long piping systems, the T's have negligible pressure loss compared to other things. It's not always true. It's definitely not always true, but a lot of the times. Okay, all right. Okay, well, I think that was the questions. I just want to make sure I got those before moving too far. So sorry, this is kind of scatterbrained. Let's get back to the idea of reference pressure, because what I want to do is show you another way on a graph to think about this. But again, you have 2 flow rates defined. That's not important for the software. It already would know the flow rate is in and out. It's the same. What this is effectively like is I like, if you think about this in terms of a pressure profile, looking at pipe friction and all of that, is we know the part of the system where you have a pressure boundary defined was right here, and a pressure boundary defined was right here, and we know a flow rate, right? We said Q is equal to something. And by the way, this is a demonstrative graph, meaning it's demonstrative, not specific to our model. It's just a graph I pulled. So we can get a pressure here. The problem happens in the middle. The pump doesn't know how much to pump up because the control valve doesn't know how much it's going to take out. So there's an infinite number of answers here. The pump, so let's say it knows the slope, meaning it knows the flow rate and it knows a total dP, but it doesn't know a starting P and a finishing P. So you can think of it as the frictional loss to that tiny portion of pipe. It knows the loss, meaning it knows the slope here, but it doesn't know where it's starting. It can start, again, it could be 1,000 PSI to 990, but there's an infinite number of answers. And by telling, let's say we told the control valve no longer it's flow control, it's pressure control. As soon as you gave it some info about pressure, it knows where to bounce back to. And because it knows where to bounce back to, and it knows the slope, it knows where your pump is gonna pump up to. So now this system becomes solvable by giving it pressure info. All right, so that's a lot of info. I said, get ready, strap in. Maybe it's not rocket science, but I'll tell you what, they use this stuff to build rockets. So is it or isn't it? I don't know. You could consider it rocket science. Hope it wasn't too much. But if you do need to come back and review these things, which I hope you do, because it's kind of silly to think that, well, we can all just remember these things from a quick webinar. It's not that simple, right? It takes a lot of repetition. We have a great help site that I like to promote where we go through topics like this. So what I'll pull up here is our help site. And what we've got here is if you land on our help site, which you can go to docs.aft.com, you can search things. So you can search reference pressure. You can search other things. In this case, I navigated to our theory area because a lot of this is theory. It's important for engineers to understand the theory. Don't do it by hand. That's why you have a software. As soon as you get 1,000 pipes, don't do 1,000 matrix math. That's ridiculous. But it's important to understand what we're doing so that you can interpret results. Anyway, we go through what I went through today. And then when it starts becoming a branched network where you have a bunch of nodes and calculation nodes, you have to worry about things like matrices and Jacobians. As soon as I see Jacobians, I'm out. That's why I use software, but you can go through the theory. And then we also go through pressure drop. This similar concept I went through today is in our help file. If you like to read words, lots of words, as opposed to watch video, it's a very detailed discussion, but certainly a good resource if you need to learn it but it's the same idea. If you just know flow, you don't know enough. And then of course, I've got to promote my own stuff. I wrote a blog on reference pressure issues where it's this similar concept, different twist on it, different way of presenting it with screenshots and words, but you can see it's very similar. This is going to be a good resource because it's not as formal. You know, it's more to be daily language in a blog, but it's the nice thing about written resources like this is you can scroll up, fast forward, rewind is a way to think about it as quick as you want. A video or a webinar can be a little hard to track through a whole hour, but we have these, okay? And again, if I share the slides with everyone, you'll have these links to what I just pulled up. Cool. And again, I went through with Fathom. The help site was on Fathom. These concepts apply to all of our products. Fathom, Arrow for steady state, and Impulse and Extreme are also steady state. You can, do a steady state solver where these these concepts apply, but they add in an extra complexity of the transient analysis if you turn that on. And transient means mass in and mass out don't exactly equal, but there are other equations to help reduce the degrees of freedom. But the idea of a reference pressure is still there. Even though it's transient, it's still there. It has to be able to solve Bernoulli's, even though it's a transient form of it, okay? All right, so let's see. Here's our contact info for you that have questions. Feel free to email in support@AFT or sales, depending on what you're interested in. If you want to buy our stuff, I guess you contact sales. If you want to ask technical questions, you contact support. Okay, let's see. I do have another question, so I'm going to hang out for just a couple of minutes because it's not quite the hour. Why does that error added pressure to? Okay, so Eric asked a question. In the software, you'll see sometimes it tells you that pressure had to be added to solve the problem. And what I will show you is if I make this control valve have to be 400 gallons per minute, meaning it's more than what my natural hydraulics would allow for, it has to act like a pump. It has to. The only way to get to 400 gallons per minute is to add pressure. And it's not realistic because if I didn't have a control valve, it only got to 288. A valve is only going to reduce flow. A valve will never add flow. So it's a warning. It says, hey, your control valve is pumping. And control valves, as we know, should not be pumping. And it's just a consequence of the math and solving Bernoulli's. Again, with these boundary conditions, the only way you're achieving 400 gallons per minute is by pumping up. Would it be safe to assume generally? Yes. Yes, so Neith is asking for pipeline networks, is it safe to assume generally want static pressure? Yes, if at the boundary there's still stuff going on. If you're tapping into the rest of the pipeline, if for instance you have a truncated model, if it's truncated where you still have pipes onward. See, that's a good pipe, I guess. If you still have pipes onward, that's static. And I think in pipelines, it's probably safe to assume the only time you use stagnation is if it's a sitting body of water, if it's a tank or a lake. Does Fathom track Reynolds number? Oh, absolutely, Stephen. So we definitely track Reynolds number. In fact, it's required to solve the Darcy-Weisbach equation to get friction. But if we go into output, I can show you right here real quick. Reynolds number is one of our output parameters. And you can see here, we're flying turbulent. But it knows this threshold of laminar versus turbulent. I think that the default is laminar is up to 2000. And then between 2000 and 4000, it's transitional, the unknown area. And then above 4000, it's turbulent. Okay. Yes, yes. Really glad the message for when pressure is artificially added. Correct. So this is because the math is fine, right? If we're just solving equations, it doesn't care. We'll solve the math you give that you give us. But then we have to put in the logic of engineering of like, okay, well, that doesn't really make sense. a control valve adding pressure, so it's a warning. So we combine the physics with the practical and what makes sense. All right. Yeah, of course. So no problem. Thank you guys for joining me and listening to me. I hope it was okay. So I will end it here. I'm going to leave this up for just a sec so you can get our contact info if you need it, but feel free to reach out. I'm going to try to gather all the email addresses of you guys that attended and send you the PDFs of the slides so that you guys have it for reference. I'll double check I didn't have any mistakes in there first though, just because it might live on in perpetuity. It would be good to get that fixed up. I don't think there was, but we'll see. Okay. All right. Well, thank you all very much. I hope you have a wonderful day and good luck with your engineering endeavors. Don't be afraid to reach out. All right. Thank you all.